Hi, happy Saturday afternoon. So we had some fun with this, right? Uh, these two proofs. Um, these two proofs. I'll leave it as we have to leave it to you as an exercise because it should be trivial. Okay. Um, uh, we're gonna have we got some other calling, higher calling. Okay. We'll get back to this. Okay, but we got some higher calling. Okay, so like because what Jesus said was Jesus said, "Hey, Peter, John, whoever, disciple, come with me now." That's what Jesus said. And some of the people that Jesus called, they said, uh, "Master, Master, give me 1 second. I want to say goodbye to my father." And Jesus said, "No, you come with me now because if you love your father more than you love me, you don't deserve to be my disciple. And whoever look back don't deserve to be with me. So don't do not look back. When there's calling, you just come." Okay, so that's what Jesus said. So let's do something similar. Uh, because, by the way, happy Sunday afternoon. I just woke up from my bed and then I was thinking about this periodicity, the relationship between periodic function and row algebra is something extremely powerful that we just proved. They're equivalent because FR, that's left hand, right hand it becomes FR. Fx is equal to FR. Fx is equal to FR. Of course they are equivalent because they are the same. Same two equations. Fx becomes Fr. Fx becomes Fr. That's why they are equivalent. Okay, so we didn't have to left direction, right direction. No, we just did left and right. They become the same equations. So, equivalent. Okay. So that's how we proved it. Okay, left hand side, left right proof, right? Left right proving technique. Uh, so what is our calling? I was thinking way back when I was in high school. That was like 1996 or something, and before that, there's this Fermat's last theorem. It was proved by mathematics professor Andrew Wiles in 1994. What grade, school grade was I? 1994. I was in fourth year in my high school. So that's when there was big news. I was in seventh grade. I mean, not seventh. 11th, no, 10th grade, Korean high school, 10th grade, when this news came about. Fermat's last theorem proved by the mathematics professor in Britain. Okay? Uh, it took him long years to prove Fermat's last theorem. But Fermat, the original Fermat, he argued that he had very simple proof, and but this professor Andrew Wiles' proof was not simple. Okay. Pierre de Fermat, Pierre de Fermat, in 1600s. Okay, he said, "I have very simple proof, but I ran out of paper space, so I'm not gonna give it to you." Okay, so it enticed many famous mathematicians to prove Fermat's theorem, where you have x n plus y n plus is equal to zn, right? Where n is 3 or more, there's no integer solution for this. Okay, that's what Fermat Fermat's last conjecture. It was conjecture then, but it was proved by Andrew Wiles, so that's why it's now not just a conjecture; it's a theorem. And so when I was in high school, I tried to prove this. I mean, after Andrew Wiles proved this, it is very difficult. Some modularity theorem I just read, or modularity lifting theorem, some elliptic curve, whatever topology. He proved in a very higher mathematics that I have no idea what they are about. And then I realized it just now. I mean, a couple of minutes ago, they're using modularity somehow. Oh, that's what we do here. Row algebra, right? Which is very, very simple algebra, row algebra. It's about modular. It's about getting rid of the MOD parentheses. Okay, that's what row algebra is. It's something very simple, very elementary. Okay, it's not higher mathematics, and but back in the days when in 1994 I was very good at mathematics. I mean, for a high school student, I was excelling. Even in this elitist Korean high school, science high school, allegedly the second best Korean high school, elitist. Okay, even when it was like the class 1 year, high school is 3 years, right? So 1 year worth of class, we had what, 6 classroom, and each classroom was like 30 students, so 180 students in our year. I was like top 10 in terms of mathematics in that elitist school, science high school. That school, science high school, is all about mathematics and science. I was top 10 of there. Okay, and when I was in Eastern Coast Ivy League, I was the best. I was number one actually. I went to PhD program, computational biology, computer science department in this Ivy League school after my undergrad in Midwest. When I was there, we take qualified exam, right? There are 5 subjects. I was the only one who passed for the first year, 4 subjects. Okay, I was number one there. Okay, and because I studied very hard. Okay, yeah, so I'm very good at mathematics. So when I was in Korean high school, 1994, I was in science high school for like 2 months. Ivy League school, I was for 2 years. Okay, so Korean science high school, I was for 2 months, 2 or 3 months. Okay, I kind of burned out, kind of studied too much. Okay, so I transferred to regular high school. Okay, so but I was ambitious too. So Professor Wiles in England, he proved in a very difficult way Fermat's theorem. Okay, and but Pierre de Fermat, he argued that he had a very simple proof, but he ran out of paper. So yeah, alas, yeah, I cannot share that with you because I just ran out of paper. We don't know whether he really had a simple proof or not. We don't know, but at least that's what he said. We know that much. Yeah, to Fermat. Okay, so I thought maybe I can come up with a easier, simpler proof than Professor Wiles have. Okay. So when I was seventh grade, I mean not seventh. Keep saying seventh. 11th grade. Seventh grade is when I started middle school, Korean middle school. 10th grade when I started high school, Korean high school. Okay, so whereas in 10th grade, 10th grade, I tried to come up with a better proof, easier, simpler proof than Professor Andrew Wiles that I read about in the newspaper. Okay, so I was trying to prove that the way I try to prove this is by I have this long sheet, big sheet of paper, like kind of presentation kind of paper, or painting paper, big paper, right? And I would make a lot of examples, with numbers, and then I realized there is some periodicity. Okay, for example, I wrote this down. Okay, so now I can erase this, right? So let's erase this. I wrote this down. Okay, so everything in this page, I've written down. Okay, so why are we doing this? Because periodicity, there's some period. I noticed some periodicity when you do the power operation. Periodicity of the ending digit. I discovered this, probably I thought about this between when I was in 9th grade and 10th grade. Okay, so because 10th grade is like Korean science high school, right? And so I graduated from middle school, Korean middle school, and before I went to this science high school as a 10th grader, there's this gap, this like about a month or two, kind of summer vacation or winter vacation actually, because Korean school, they don't start in August, they start in January. That's where school year starts. So there's summer, I'm not summer, but winter vacation between the previous year and next year. Okay, so I graduated from Korean middle school, and I was about to go to this elitist Korean high school in January. We graduated, I guess, December, I guess, right? So there's this about 1 or 2 months winter vacation, and that's when I started starting to study, research, investigate on my own, to come up with a easier and better solution, proof for Fermat's last theorem. I wanted to find out something easier than Professor Wiles' proof when I was 10th grade. I mean, between 9th and 10th grade. So I did a lot of investigative research on my own. By research, I didn't look at other books. I just made a lot of examples on my own. I didn't study anything else. I just studied on my own, without any other books or website. No, just making examples. That's just like what we are doing here. Okay, that's what I did in that winter vacation between middle school and high school. Just before I entered that elitist science high school in Korea, during the winter vacation after middle school graduation. Okay, so and what I discovered is that there's some periodicity there. Okay, that's what we are doing here. Well, why we are doing Fermat's theorem all of a sudden, because I noticed some periodicity there. Okay, and later on I went to this Korean science high school, elitist school. I was there for 2 months, and this elitist school, mathematics high school teacher in this elitist Korean science school, he told us a little bit about that kind of periodicity. So then I realized, okay, it's a well-known phenomena. Okay, periodicity in, what do I mean? Yeah, let me illustrate it to you. Let's use blue. Uh, it's a periodicity of the last digit. Okay, so that's I heard it mentioned briefly by this elitist Korean science high school teacher. So I realized later on that it's something well known, but before then I didn't know whether it was known or not. I kind of independently rediscovered that phenomena. Okay, periodicity when you apply power operation. Periodicity is very last digit. Okay. Uh it has to do with number theory. Okay, so it's like this. Let's say you have 9. Okay, 9 squared is equal to what? 81, right? Okay, and 81 squared is what? Blah 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 1. Okay, because you multiply 81 by 81, right? We'll do it. 81, 8, 6, 4, 8, right? Add 1, 6, 5, 6. 6,000 something, right? So this is 81 times 81, okay? Okay, you have 9, and you have 9 squared, and 9 to the third, 9 is 9, is what? 81 is what? Dot 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 9, okay? And 9 to the fourth is 81 times 81, is dot 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 1. 9 to the 5 is dot 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 9. That's what I'm talking about, okay? So I try to attack this famous last theorem. I try to prove this in terms of this periodicity in the last digit of these powers. That's how I approached going about proving this famous last theorem. And then I gave up, okay, because somehow it was not working. Okay, so but at least I tried it that way. Okay, so I didn't learn this from anywhere else. I independently or rediscovered this periodicity in this power operator application. Okay, so we're gonna explore that. That's what I refer to as calling. Okay, why? Because there's what's called as Beal's conjecture, BEAL. He's a banker, amateur mathematician in America. Okay, I ran into his name when I was looking at the list of amateur mathematicians. So yeah, Wikipedia they're doing fine job. Okay, I mean, if they include everybody in that list of amateur mathematicians, it will be too long a list. The list will be too long. So it's better if my name is not included there, because then everybody's name will be included, because I'm kind of underdog, small guy. Uh, so Wikipedia they do this harsh vetting process, very very high standard, including that Texan Hispanic lady. They're doing fine job, okay? They're justified. Alright, so but they can be nicer to us, people like us. They didn't have to be cruel and harsh like that. They didn't have to be rude and mean like they were to me and to other people. They don't have to be mean. They can be nicer. But hey, nobody's perfect, okay? And they don't get paid by Wikipedia. They were volunteers anyway. So, or maybe they do get paid. My guess is that they don't get paid, okay? Because Wikipedia is kind of ghetto, voluntary, charitable, whatever. So We'll take a shot at proving Fermat's last theorem using perhaps row algebra. Okay, because row algebra is very good at dealing with periodicity. All right. Uh, I just learned 10 minutes ago, 30 minutes ago, Andrew Wiles used some kind of modularity arithmetic, because modularity theorem and modularity lifting, that's what he used. I learned like 30 minutes ago in Wikipedia. I didn't know. I didn't until 30 minutes ago. Okay. So I looked up what is modularity theorem, what is modularity lifting, and it has to do with elliptic curve. Elliptic curve, I read about that term, heard about that term back in 1994, around that area, around that time when I was in South Korea, because I was curious how Professor Wiles proved that Fermat's theorem, and that's the first time I heard about it, and till today I have no idea what that is. Some higher calculus, I guess. I looked it up every now and then, but it was way above me. Okay, it was too much to learn. So I don't know what elliptical curve theorem, modularity theorem, modular lifting technique. I don't know what they are. I looked it up, but it was way above me. Okay, my way above my level of mathematics. So I'm not going to try to learn it. Okay. Cool. So the way I attacked back in 1994, after I read this article, news article about Professor Wiles having proved this Fermat's theorem. Yeah, you know what? I think I can do it better way, simpler way. Okay, so try to prove this the way I try to approach this proving Fermat's last theorem. So basically, it says this x, y, z uh, belong to what natural number, you know, which is non-negative integer. It doesn't exist. This x, y, z doesn't exist when n is 3 or more. Okay, that's the condition. This x, y, z doesn't exist. And then later on, Mr. Bill, banker, financial. I think he's from Michigan, from what I read. He's American, okay? He's an amateur mathematician, so I ran into his name in Wikipedia's list of amateur mathematicians because clicked every single one of them, okay? Because I was very curious. I'm an amateur mathematician, but those amateur mathematicians, Wikipedia, the list, at least they are more known than I am because I tried to put something up there, but they rejected me. So in a sense, they are better amateur mathematician than me. At least they are more known than I am. Okay, so including the American ex-Marine, the Marine veteran guy, MKS, something like that. I don't remember his name, but his initial I don't even remember. It's something like MKS or something. MKS constant, something like that. I I should look him up and find out what his initial is. Okay. We'll take a break. Okay, so that's Fermat's theorem statement. Mr. Bill, he generalized this even further. Okay, and he has $1 million prize. Prove or disprove the Bill's conjecture. $1 million. And yeah, it's kind of enticing. What a nice guy to encourage mathematics. That $1 million is like a scholarship fund that he established, basically. Okay, so Bill's theorem, yeah, he generalized this Fermat's theorem in a particular direction. Okay, I don't quite remember what exactly it was, but what we're gonna do is we'll try to prove again Fermat's theorem using our row algebra. Okay, at least we'll try. Okay, and then we'll go after the Bill's conjecture because we can, I can win, or we can win together. Okay, $1 million. Okay, so that's kind of interesting. Yeah, I can use $1 million. Will I share that with you? I don't think so. I just take. So what do I do with $1 million? Well, I pay the tax first. Probably the tax rate will be like 50%, so I'll be left with 500,000. Yeah, I can use 500,000. What will I do? I just put in my bank account. Nothing will change. Not a single thing. I put in my bank account. It'll be a rainy day fund. I don't need that kind of money. I would just put in the savings account and use it as a rainy day fund in case of emergency because nothing will change. I promise you. Nothing. Okay? Yeah. Well, that'll be interesting. What a nice guy, Mr. Bill. What a nice guy. He's kind of philanthropist, kind of. That $1 million of his own money, that donation, is like he giving out money for scholarship. Okay, he's what a nice guy. What a good American, good Samaritan American. Okay. We take a break and first step we'll try to prove Fermat's last theorem using row algebra. Okay, because uh, I still think, if not believe, I still think, and probably there's easier way to prove this Fermat's last theorem than what Professor Andrew Wiles did, using all those fancy mathematics. We'll try to prove this using row algebra. So because I tried and I gave up when I was between ninth and 10th grade back in 1994. That's when he came up with the proof. He published his proof in 1994. Yeah. I tried and failed. I gave up. Okay, because I learned something about this periodicity. Then I realized ah it's too much. But now that I have time, why? I have a full-time job. When I was in this Korean science high school, and 2 months after I went to regular Korean high school, Korean high school, whether it's elitist or regular public school or private kind of boarding school, yeah, South Korea have some of that boarding school, dormitory kind of high school. You are too busy. 80 hours a week, kind of. Well, you work in Manhattan. Are you a lawyer in Manhattan? Like some of my friends, Washington D.C. You work in Wall Street. Yeah, you pull 80 hours a week, right? That's Korean high school. Korean high school students, if they are very high performing students, yeah, 80 hours a week kind of studying. Okay, that's how it was back then, at least. We studied 80 hours a week, twice as full time worker. So, so I had no time. I had to let this go. But now that I would just work 40 hours a week, regular. Okay, so I have 40 hours a week time to do this, and I know more mathematics than, by far more mathematics than I knew in 1994 when I was 10th grade high schooler. So we'll tackle this. We'll try to come up with a easier proof of Fermat's last theorem using row algebra. Okay, so I think we can do this. Okay, if we reproof, reproach reprimand. We're not talking about that. Well, sure, discipline, whatever. But it's been already proven by Professor Wiles. But we believe we can prove this in a simpler way, easier way. We'll take a shot at that. Okay, so after that, we'll go after Mr. Bill's conjecture because that's more generalized statement from. I mean, you can generalize Fermat's last theorem in multiple different directions, but Mr. Bill's generalization of Fermat's proof, Fermat's last theorem, is just one particular generalization of that. I'll tell you all about it. Okay, I'll tell you all about it. Different direction of generalization. What I mean by that. I'll give you some examples out of this. Okay, but we'll take a break. Okay. Now we are like, excited. Good. We need some of that juice, right? $1 million, thanks to philanthropist, Mr. Bill. Okay, what a nice guy. What a nice guy. Donating his $1 million money for the advancement of number theory in mathematics. See, not some. There are some good rich people. Okay, not don't hate people just because they are rich. Because there are some good rich people. Okay. So. Okay. Um, okay, we need to. We have this. We know a lot of mathematics by now, right? We have this approach to mathematical proof. We first make a lot of examples with concrete numbers, and then we find some pattern, and we come up with some theorem, formula, conjecture, hypothesis, and then we prove it, right? So that method has been working for us time and again. So we'll do the same thing here, okay? Periodicity, okay, so, okay. How exciting, huh? Because I Fermat's theorem is like number theory, but it involves some calculus, at least in uh, Professor Wild's proof. So I didn't quite want to go there. I mean, I know good enough calculus, but I dealt with it enough times so it made me, I'm kind of fed up with calculus, okay? Because I dealt with it so many times before in my past. So I didn't want to go there, okay? So that's why I kind of stayed away from this famous last theorem. Okay, yeah, I was kind of thinking about Fermat's last theorem because it's a famous theorem in number theory. So should I should we should I study Fermat's last theorem a little bit? No, I'd rather stay away because Professor Wild's proof of Fermat's theorem, it was involved a lot like higher calculus that I have no idea was about. Elliptical curve theorem, elliptic theory, whatever. Oh, no, I'm not doing that. Too much calculus. I don't even know what it is, and do I want to learn? No, I rather not. I rather learn some foreign language like Russian. Okay, because I want to be balanced. Anyway, okay. So periodicity, the power of nines has periodicity of 2, 9191. We are just talking about last digit. 6561. We don't care all the other digits. We only care about very last digit. Okay, that's how I approach to attack this problem of Fermat's last theorem. Just looking at just last digit, add them up. Can they be the same? Okay, that's I was like just before 10th grade, between, okay, let's say 9.5 grade during the winter vacation, because Korean school year starts in January. Okay, so maybe in February, I don't know. I was like 9.5 grade. How old was I? Ninth grade, 13. I was like 13, 14, 12. No, not that. I was, so 12, when I was 12, I was in 6th grade. So 15. Between 16 and, so 13, 14, 16, 13, 14, 15, that's middle school. 16, 17, 18, that's high school, right? So 13, 14, 15. I was like 15, 16, 15.5 years old. I was like 16 years old, okay? Looking back, it was kind of smart of me that I tried to attack this Fermat's last theorem by just using the last digit and the periodicity of these powers. It was very smart of me, actually, looking back. I was just, what, 13, 14, 15, okay, 15.5 years old. 15 years old, 16 years old. looking back, that's very smart of me to thinking this. Or taking Fermat's last theorem, just using the last digit, periodicity thereof, or powers. It was very smart of me. Because I didn't learn that from anywhere else. Okay. I uh, I studied a lot of mathematics then. Okay. Well now, yeah, we are doing that too. But of course, it's God's blessing. Yeah, he God blessed me with all this wonderful mathematics, numbers. But you have to understand, I didn't always like mathematics. Okay, when I was fourth grade or second grader, I was about average or even less than average because I didn't want to memorize this multiplication table and all that shit. But I had to learn it because Korean public school, like elementary school, middle school, high school, 12 grade system, probably is modeled after American public education system. And in Korean public school system of 12 years, you don't have electives. Everything is mandatory. They have this set syllabus, coursework, curriculum. Everything is mandatory. So, and they have Korean education system, at least back then, was highly, highly mandatory and very disciplinary, and we didn't have any choice. We had to learn. Okay. So yeah, I was forced to learn mathematics, arithmetic. So, and I was not doing very well because I was more interested in playing as a boy, hanging out with my friends, pranks, whatever. But I was forced to learn, so I hated mathematics. But my family members, my parents, my siblings, my grandparents, they taught me mathematics, arithmetic. Okay, so and my friends. So yeah, then I came to like it. At first, I hated it. Okay, so, because I was forced to do it. After that, I came to like it, enjoy it. Okay, and I excelled. Later on, I excelled. I became very good at it, and I came to love it. Okay, so that's my phone vibrating. Okay, we'll explore periodicity in powers. Okay, so okay, let's do that. Okay, 1 to the 1st. Well, we'll start from zero. 0 to the 1st. Well, we know 0 to the nth is 0. 1 to the nth is 1, right? How about 2? 2 to the 1st is 2. 2 to the 2nd is 4. We can stop there because from there on it's the same. Two, we only are interested in the very last digit. You wanna go on? I'll do it for you. Because 2 power of 2, I memorized this shit. Why? Because I major in computer science in 4-year college, university, state school, somewhere in Midwest. Okay, I major in computer science. So yeah, we all deal with this power of 2. So I memorized this crap. Okay, so 2 to the 10th, yeah, is this 1 kilobyte, right? I memorize this crap. Okay, so we just look at the very last digit. periodicity. Yeah, the periodicity of last digit is 1, 1. Now here, 2, 4, 8, 6. 2, 4, 8, 6. Okay, so periodicity 2, 4, 8, 6. Okay, so periodicity is 4 when it comes to power of 2 to the n. Okay, so there's periodicity. That's what kind of caught my attention. This periodicity, row algebra. Okay, so because after I took a nap today, Sunday morning, I woke up and then because earlier this morning we proved something significant. The connection between periodicity and row algebra. We call it we named it periodic function theorem. Before that, preliminary periodic function theorem. And then after that, using PPFT, preliminary periodic function theorem, we proved full-fledged periodic function theorem, the connection between periodic function and row algebra. We just change plus into row. Okay, we proved that shit. And then after that, I fell asleep, and then I was lying on my bed for a while. Then I can't remember. I guess it's with the help from God, Holy Spirit, angel, who's living in this house, I guess, with me. Just kidding. I'm just kidding, okay? Yeah, I can't remember back in high school, when I was in high school, before the high school, between middle school and high school. Yeah, I tried to prove that Fermat's last theorem and using the periodicity of these powers, using just looking at just the last digit, That was kind of smart of me. And periodicity in Fermat's theorem, my attempt to prove it, periodicity. Yeah, later on, the same thing, periodicity. In this elitist Korean science high school mathematics teacher, he mentioned this during his lecture. Okay, so then it's already known. But I came to this conclusion, this discovery on my own. Between middle school and high school, when I was like 15.5 years old, in my teen, 15 years old. So I can't remember that. Okay, so yeah, that's how I came about this. Okay, so I did this already when I was like 15 years old. Okay, because it's elementary. It's not higher mathematics, no. But I did discover this periodicity. Okay, all right. Let's keep moving on. How about 3? 3 to the first is 3. Should we start from 2 to the 0? No. You don't have to start from 2 to the 0. That 2 to the 0 is 1. But because there is no 1 here, okay, in this periodicity. It's 2, 4, 8, 6, 2, 4, 8, 6. There's no 1 here, okay. We can stop right there. Okay, so 3971, 3971. Okay, so 3971. Periodicity 4. Okay, let's go to the next. We'll go to from all the way to 9. Okay, because from there on it's all the same. Okay, so yeah, it's a lot of legwork, but I have time. So unlike when I was in high school, Korean high school, 80 hours a week kind of studying. No, I didn't have time for this yet. Okay, so it's good that I have time. I just have full time job, 8 to 5, 1 hour lunch time, 15 hours break in the morning and in the afternoon. After Monday to Friday, time is mine. Okay, so it's good that I'm no longer Korean high school. It's good that I'm not a stockbroker or in Wall Street or lawyer in Washington D.C., Chicago, Manhattan. They work like 80 hours a day. Okay, and it's also good that I don't have any girlfriend. Okay, so I have free time alone in Alaska. Okay, it's good that I'm alone in Alaska. Okay, so because I can devote my time for mathematics. Good. All right, we can stop right here. Periodicity 2. 5. Right, that's easy, right? We can stop right here. Periodicity 1, okay? Okay, let's keep moving on. 6. Periodicity 1, okay? We are just looking at the very last digit. Okay? I don't have to do this whole multiplication, okay? I can use a dot, 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 something, okay? We'll do that, okay? So we don't have to do entire multiplication, alright? So we're just looking at the last digit, okay? Yeah, just looking at the last digit of this multiplication, it was very smart of me. I was just like 15 years old. I mean, it's not that young. It's not like I'm Mozart who started playing violin and start composing like orchestra, this concerto, opera when he was like 7 or something. I don't know what age he was, but yeah, I was in my mid-teen, like 15 years old. So, but I was very good at mathematics. Okay, so but looking back, it was very smart of me to attack this problem of Fermat's last theorem by just looking at the last digit of these powers. It was very smart of me, okay? So, kind of ingenious. And I didn't learn this from anyone, okay? Of course, I learned a lot of mathematics. Okay, so I was very good at mathematics. I learned many mathematics. So, but this idea, just by looking at the last digit and periodicity, is I didn't learn it from anybody else. Okay, so it's something God gave it to me. Okay, so sure, yeah, God's gift. Okay, yeah, 3 times 7. What is it? Dot 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 1. Okay, 7 to the fifth. Dot 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 5. I mean 7. Okay, so we have periodicity here. Okay, periodicity 4. All right, so we got 7 down. How about 8? We got two more to go. Okay, so we have 64. We know that. Dot dot dot. When I do multiplication in my mind, I use Korean because Korean number from 0 to 10 is all single one syllable like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's single syllable, so it's easier for me to do multiplication and in Korean language because it was single syllable from 0 to 10. Okay, so dot 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 2. All right, 8 8 times 2 dot 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 6. Right, 8 times 5, 8 to the 5th. 6 times 8 dot 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 8. Okay, we got periodicity right here. 8, 4, 2, 6. Okay, so that's periodicity. You just repeat itself. Okay, how about 9? Number 9, like in the Beatles, number 9, number 9, number 9. We know that because we did before, right? 5, 10 minutes ago, 20 minutes ago. Okay, so yeah, we just fit it right here. Okay, so 9 to the first is 9. 9 to the second is 81. 9 to the third, dot 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 9. Okay, so 9, the power of 9, it has periodicity too. So periodicity can be 1, 4, 2. Periodicity can be 1, 2, 4. That's it. Periodicity of the last digit of all these powers of any number in the world, because it only depends. You have 100 and 100, 237 to the nth, right? You only need to look at the last digit. Okay, the periodicity of this 237 to the nth, it only depends on the last digit. And what's the periodicity? 4. 7931, 7931, 7931. Okay, that's how I try to attack, how to try to prove this famous last theorem when I was like 15 years old. So it's not. I'm not saying that I was smart or ingenious. No, it's God's gift, and also I worked very hard to learn mathematics. Okay. I'm not now 41 years old. I'm not a 40 years old virgin. No, I'm not a virgin. But look at me, okay? Sunday morning, okay? It's not like I had this lady next to myself in my bed. No, I'm a loser, geek, nerd by all standard. But I know a lot of mathematics, more mathematics than when I was 15 years old. I'm 41 years old. So since then, for 25, 26 years, I learned a lot of mathematics. Okay, so when I was 15, yeah, I had to go to this science high school, and after that, regular high school, because I transferred to regular high school thanks to nice people in the science high school, they let me transfer. Okay, oh, it was too much. Let me go to regular high school, and they let me. Okay, and regular high school they accepted me. So thanks to both of them, elitist high school and regular high school, they are all nice people. Okay, so but in both schools I was busy, 80 hours of studying. Come on, give me a break. So I didn't have time to develop this approach to attack this famous theorem. And also, I didn't know enough mathematics. But by now, I'm 41 years old. I know more, by far more mathematics than I did when I was in, as of compared to when I was 15 years old. And now I have more time too, because I was just work 40 hours a week, and I don't have any girlfriend. I don't have any wife and kids. No obligation. Okay, time is mine. Time enough at last. Just like Twilight. I'm not gonna tell you. I'm not gonna be a spoiler. Okay, time enough at last. I'm not gonna tell you how the story ends because I don't want to be a spoiler. No. Okay. Time enough at last. Twilight Zone series. Go ahead and look it up. Okay, or buy their DVD. We'll take a break. Okay, so we continue this. This is interesting. God, thank you for calling our attention to this because this is exciting. Okay, not because of this $1 million award for this Bill's conjecture. Yeah, that's great motivation because we all want money, rainy day fund. Yeah, God bless that gentleman, his family. Okay, because he's a philanthropist. That's his donation, you know. Yeah, scholarship fund. God bless him and his family. In Jesus Christ's name, amen. Okay. Yeah, nice guy. Yeah. But beside Bill's conjecture, this $1 million award, yeah, Fermat's last theorem. That's what we are doing. Okay. Because we think we can prove Fermat's last theorem using raw algebra. Very elementary, very easy. So yeah, that's all the time. Okay, so take 5 minutes break. Okay, so it's something very interesting here. Okay, so take five. Okay. Yeah, it's a reproof, brand new proof, easier proof. It's already been proven by Professor Wiles in England, the Great Britain. Okay, but we think we can do better. We think we can prove this in a more easier manner. Okay, so take five. Okay, using the algebra. Let me charge my phone because yeah, it need to be charged. So could be a mirage. Do you know what mirage is? Mirage is a optical physics phenomenon. You are wandering in desert land and you see water. Water. Oh, I'm thirsty. Oh, where's my water? Oh, your lips are blistering and give me water. I'm in a desert land. Gobi Desert in Asia, Mongolia, China, or Sahara Desert in Middle East, North Africa, okay, whatever, wherever you may be, okay. Water, give me water, if you're like me, alone in Alaska, give me vodka or give me some girls. Where's my girlfriend? Date. I'm thirsty for sex or for alcohol. So it could be a mirage that I'm smelling some land. Oh yeah. Let's say you're in the middle of ocean. Are you a sailor? Sailor? Do you have a boat? I don't. I don't have money. Yeah, in the middle of ocean. Yeah, you have plenty of water there, but it's salty water. You don't want to drink sea water. Water everywhere, but there's not clean, unsalted water. Okay, so where is water? I want to get into land, so that I can find some pond or river, waterfall, drink some fresh water. Where's water? So and then you're in the middle of this ocean and you see some seagulls, and then you can, oh, the seagull. There has to be this island, treasure island. Yeah, I see the seagulls, so maybe island or continent, which is a big island. Maybe somewhere near. Okay, so yeah, I smell some land. It could be a mirage, optical phenomena. This temperature difference between upper and lower. So this water, I see it. Oh, so it could be a mirage, but I'm smelling that there's land nearby in this exploration. Okay, because in in mathematics, there's proof by cases, exhaustive enumeration. Yeah, we can do that. How many cases do we have? What? 11, 10? 0 to 9, yes, there are 10 cases. And Fermat's theorem, okay, x to the nth plus y to the nth is not equal to z to the nth. Okay, that's what we need to prove. When n is 3 or more, comma, x, y, z, they all belong to what? Some natural number, right? Which is same as what? Integer, not zero. Integer 0 plus, integer plus, okay, so yeah, non-negative, well, positive integers, okay, natural number. I mean, come on, there are 3 terms, right? We can do exhaustive addition, right? What we gotta prove is that they are not equal. Okay, so yeah, we can do that. That's exhaustive enumeration, right? So easy, right? Because in this base 10 system, 0 to 9, base 10 system, the last digit of any number in this base 10 number, the last digit is from 0 to 9, okay? And we have periodicity. So it shouldn't be very difficult to exhaustively enumerate this in terms of last digit, okay? So that's the approach I took when I was in 9th grade, between 9th and 10th grade, when I was like 15 years old, okay? So, and I gave up. Why? Because I was too busy preparing for this elitist science high school in South Korea, Seoul. Allegedly, the second best, not first, but second best Korean high school. Okay, back then. Oh well. Before we get into that, let's slow down a little bit. I will tell you about direction of generalization. Okay, we can generalize the famous last theorem in multiple ways. Okay, uh, let's use black. Okay, so famous last theorem. Well, it was expressed in equality as opposed to inequality, but actually it's inequality. Okay, this whole thing is inequality. Okay, there's no such numbers, right? But yeah, generalize this. You can do this x I to the n sigma I from 1 to k, which is equal to x1 to the n plus x2 to the n plus x3 to the n plus dot 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 plus xk to the nth is equal to x k plus first to the nth. Okay, yeah, it's one possibility of generalization. Okay, but you can generalize this Fermat's last theorem equation in a different way, another way, just like Mr. Bill did. Yeah, he's good mathematician, amateur mathematician. He's a banker, so he's good with numbers. He's a philanthropist. Okay, scholarship fund. Yeah, we appreciate that. Okay, so the way he generalized this thing was I have to look it up. Okay, my phone is charging. Okay, but let me try to remember. I think he generalized this something like x to the a plus b to the something like y to the b is equal to z to the c. Is that how he generalized? Let me grab my phone. It's charging, but Bill's conjecture, Mr. Bill's conjecture, yeah, banker, financial. Let me grab my cell phone. It was in my pocket of that jacket. Pocket of the jacket. It wasn't even charging. It wasn't even charging. Bill's conjecture. What is that? MRB. Yeah, that's the veteran Marine, U.S. Marine, ex-Marine veteran. MRB constant. Yeah, okay, so that's it's not MK. It's MRB. Okay. All right. Mr. Marvin Ray Burns. Mr. Burns. I guess he's a white guy. Andrew Bill. Mr. Andrew Bill. Okay, so Bill's conjecture. Bill conjecture. Okay, let's see that. Yeah, it's like yeah, X Y Z A B C is kind of swapped, but yeah, that's basically that's the direction he took. Okay, so well, just to honor him, uh, translate that because X, Y, Z, and A, B, C they kind of swapped, you know. So they're all positive integers, natural numbers. A, B, C they are what, more than two, three or more. Okay, so just like in Fermat's last theorem, and X, Y, Z has to be co-primes pairwise, meaning the GCD is 1, okay, for all this between X, Y, and Z. So that's why we had to do this because we are studying Euclidean algorithm, GCD, okay. Uh, it's like our manifest destiny. We have to do this. It's not just about $1 million, okay. No, we have to do this because periodicity, row algebra, we are too involved. It's too late for us to back off. Okay, so we have to do this, explore this. Okay, if we win $1 million, that's good. But I'm not gonna give it to you. I'm not gonna give it to any charitable donation. No, no. I just put it in my bank. I will pay the tax, probably like 50% of $1 million. 50% is five. I'm left with 500,000. I put it in my bank. Okay, so rainy day fund. Nothing changed. I don't think. I go to work, pay my bills, debit. Okay, so yeah. Anyways, so yeah, several different ways to generalize this. You can generalize in terms of the number of X, Y, and Z. Okay, or you can generalize in terms of N. That's the particular direction that Mr. Bill took. It doesn't have to be N and N. It could be A, B, C, different numbers. And he put some another constraint, condition, restriction, rule. X, Y, and Z has to be co-primes. Their GCD has to be 1. Okay, so give me 1 second. I gotta have some Toms. We have too much vodka, I guess. Okay, let's back on track. Emmanuel, okay, God is with us, alright, so let's do exhaustive enumeration to prove Fermat's last theorem, okay, because it shouldn't take that long, okay, so. I mean, you pick 2 out of 10, okay, so out of 10, you pick 2. It's combination. Okay, what is it? 10 times 9 divided by 2. Ooh. 45. It's a lot of legwork, okay, but we can do it. That's probably why I gave up because I was preparing for Korean science high school. I was too busy for this elitist school, and that's why you guys fail, elitists. You are too busy. Okay, you are in what, MIT, Harvard, Yale. I was in those. Not I never went to those schools, but yeah, actually I was in Ivy League, lower Ivy League school in America for 2 years. But Yeah, you guys are too busy, so you don't have time to do this legwork, humble job, right? But we'll do it, okay? So it keeps me out of trouble. It grounds me. I'm not drinking and driving. I'm not going to the street and fight people. No, I'm grounded, okay? So being busy is good. It keeps us out of trouble, right? Yeah, idle hands is devil's playground, right? I'm not getting any girls and get STD or okay. So there are 45 possibilities. It's like this, okay? So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, okay? And you pick two. I'm gonna take a picture of this. It look like seashell, right? And then from two, from three, you have yeah, this thing, this seashell, okay, is total of that is 45. We can do it, okay? Because we have time, alright? Let me take a picture of this shit. It's kind of pretty. I'm not gonna write this shit down, okay? Because it's too much to write down, but at least I can take a picture of this. I have to find some right angle to take a picture of this. Oh boy. 3 shots, okay? So I'm like, smile. How about I take a picture of you? Smile. Ah, boy, how do we go about this crap? Well, uh, it's overwhelming, right? 45 possibilities. Oh, that's a lot. And it could be actually more than that. It could be 10C3 binomial coefficient, okay? Because you have X, Y, and Z. Okay, so 10C3 was that? Oh my goodness, that's like 10C3 binomial coefficient. Okay, 10C3 is like where you have 6 downstairs and 10, 9, 8. Where there's like 3 here, 4 here, 120, right? Oh boy. But we have time, okay, don't worry. So we can do it. Okay. It's just 120. Come on. How many times do you drink water? How many times do you breathe in and out a day? I don't know. Couple of thousands. We can do 120, okay? It may take a month, a week. 120 is not too bad. maybe it's less than that. Okay, so let's just go after this guy. X to the third plus y to the third plus z to the third. Okay, I mean it's not equal to this to the third when x, y, z. Uh, we just focus on positive integer. Okay, so okay, we reduce 10 to 9 from 1 to 9. Okay, so good. Natural number, which is same as positive integers. Okay. Plus, it looks like cross, like Jesus Christ, crucifixion. Okay, so yeah, we are crucifying ourselves, sacrificing for humanity. Sure. When we could have gone to dating and have sex, we are doing this mathematics. As opposed to having sex, we are doing mathematics. As opposed to doing crystal meth, like drugs, we are doing mathematics instead. Okay, so instead of methamphetamine, we are doing mathematics. Not math, but math. Not METH, but MATH. Okay, so let's take a break. Okay, so we do take frequent breaks. Are we addicted for breaks? Sure. Well, no. We drink water, we breathe in air. Can you say that's addiction? No, it's necessity. Necessity. Okay? Alright. Take 5 minutes. Let me charge my phone. Okay, we're back. You know, I study a lot of mathematics, so I know mathematics community is very conservative. Okay, so they will say, "Oh, you cannot just write an equation and say it is true. You have to prove it. It has to based on this existing, established mathematical theorems, establishment. You have to base honor your parents, your ancestors." You know, yeah, I know. Okay, this. Let's take a break from mathematics, shall we? About aging, ages. We talked about this probably before. Okay, metaphysical aging, metaphysical age. I'm a Generation X, Generation Xer. Okay, so was born in 1970s. I'm 41 now, so I belong to Generation X. Okay, but me and Euclid, Mr. Euclid, okay, in what several centuries BC, before Christ, I guess. I don't know what is Greek mathematician. I know more mathematics than Mr. Euclid, in a way, because since Euclid, Mr. Euclid, there has been a lot more development in mathematics, and I learned it. So, what year did he die? Maybe 200 BC, right? Before Euclid, yeah, there were other mathematicians, and he learned from his predecessors, right? But after Euclid died, Mr. Euclid died, there have been thousands of other famous mathematicians like Euler, Gauss, Newton, Leibniz, you name it, okay? And I learned all this further later developments since Mr. Euclid passed away. So I know more mathematics because I got benefit from mathematicians after Mr. Euclid passed away and went to heaven. Okay, so I'm pretty sure he's in heaven. We all have dirty skeletons in our closets. Okay, so who knows what Mr. Euclid did when he was not doing mathematics? Okay, we don't know. Okay, so but by and large, I think he's a good man, diligent man. I'm pretty darn sure that he's in heaven, not in hell. Okay. So, me born in 1970s in America. Okay, yeah, I was born more than 2,000 years after Mr. Euclid was born. So in a way, Mr. Euclid, he lives on his legacy. So he's by now more than 2,000 years old. His legacy, the elements. I don't know. The element, yeah, tomato, whatever, potato. Okay, so. I was born in 1970s. Okay, I'm not gonna tell you exact what year it is, but I kind of gave it away to you. It's 2019. I'm 41 years old. So subtract it. What year was I born? Simple mathematics, right? But yeah, you may say I'm younger than Mr. Euclid, but in another way, I'm older than Mr. Euclid because just because I was born 2,000 years later, I inherited that 2,000 more years of mathematical knowledge than Mr. Euclid had 2,000 years ago. Okay, so I'm older than Mr. Euclid in a way because I inherited more. Copium knowledge level is a lot higher in me than Mr. Euclid. Because since Mr. Euclid passed away, there have been other more mathematical advancement, and I benefited from that, like calculus, logarithm. Okay, so I don't know too much about group theory. Okay, so topology, I don't know much about it. I know a little bit. Okay, we'll prove this Fermat's. We'll take a shot at proving Fermat's theorem when n is equal to 3. Okay, so it's proof of inequality. It's not equality. Okay, so it's inequality. So mathematicians, they're so wrapped up with equality. I guess they're kind of liberal that in that sense. Okay, but it's inequality. Okay. There's so many possibilities here. Okay. One to the third is dot 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 one. So we just call it d one. Okay. Dot 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 prior digits, we just call it a d instead of doing dot dot dot. Okay, it's simpler. Okay. 2 to the 3 is dot 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 8. Well, dot 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 1 dot 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 2 dot 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 3. Okay, so okay, dot 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 3 to the third is what? Dot 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 7. Dot 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 4 to the third is dot dot dot, well, some different dot, so we call it d prime. Okay. 4. Dot 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 5 to the third is some other dot dot dot, some d prime 5. Okay. Dot dot dot, we're running out of space now. So third is what? Yeah, d prime 6. Dot 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 7 to third is some other dot 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 3. And yeah, we'll do one more. Okay. Okay, that's exhaustive enumeration in terms of power 3, right? But we don't have to do to infinity in terms of n power, because we have periodicity. Okay, that's where probably row algebra will come in handy. Okay, we don't have to do to infinitum, add infinitum. No, we have row algebra. Okay, so we have, because we have periodicity there. Okay, so but that comes later. All right, we are just doing when n is equal to 3. Okay, so Fermat's theorem. Okay, x to the n plus y to the n is not equal to z to the n when n is 3 or more. Okay, so it's not equality, it's inequality. Okay, so for all these centuries, by now 5 centuries, mathematicians, they did it wrong. It's not equality. Fermat's theorem is about inequality. Okay, there does not exist this triple, Fermat triple. So it's inequality. Okay, so yeah, just completed. X, Y, Z, they belong to natural number. Okay, so yeah, it's inequality. It's not equality. It took humanologists to correct that wrong for centuries. Isn't that kind of pretty back there? Yeah, it's Alaska. By now, what time is it? Maybe 3 o'clock in the afternoon. Oh, Alaska is beautiful. All right, so yeah, we already found some counter example. 1 plus 8, it could be 9, right? So, and they are same. They are not unequal. They are equal. Okay, so we have some problem here. All right. Yeah, I guess that's why I gave up when I was 15 years old. Oh well. What I'm saying is this X Y Z, right? So some is green. Okay. So maybe this approach doesn't quite work. Okay. So oh well. But we tried. Okay. So some number to the third plus some number to the third, it can be equal 1 plus 8, 9. Okay. It can be equal to some another number 9. Okay. Why? It could be equal because this is what d prime 1 plus d prime 8. Yeah, it could be d prime 9. We'll give it some subscript. Okay, 1, 2, 3. D prime 1, D prime 2, D prime 3. Actually, we will call this D prime 9. Okay. Okay. All right. So that's possible. So that's counter example to our approach. So our approach failed miserably. I'm sorry. We tried. Okay. So hmm. But we are not gonna give up yet. We're not gonna just fold it up. Okay. So because we are hardcore. We have time. Okay. We are doing like row 10. Okay. Mod 10. Okay. Kind of. Because what if we add these two guys? 8 and 7. 15, right? So then yeah, you can we can find some number 5 right here. Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0, 1, 2, 3. Isn't that interesting? This may take very long time, okay? But it appears all every single digit in base 10 system from 0 to 9 is appearing only once here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How interesting. Is it true for all power number? What if we do this number 4 or number 2? Well, we don't do number 2 because Pythagorean theorem, right? Somebody proved, I think, the infinite number of Pythagorean triples. Okay, x to the second, x squared plus y squared plus is equal to z squared. I think somebody proved that there are infinite triples. Pythagorean triples, okay? Like 3 squared plus 4 squared is 5 squared, right? So we don't deal with 2, but third and on, how does that work? When it's fourth? Well, let's take a look. Well, so you have 0 and 1, right? And you have 6, 1 again, and 6, 5, 6, 1, 6, 1. Okay, okay, so when n is equal to 4, there's only 0, 1, 6. How interesting. Wow, surprising. Mathematics is a never ending story like labyrinth, Alice's Wonderland rabbit hole. Okay. We find brand new whiteboard after a break. Okay, we'll do it when n is equal to 4. Okay, like x to the fourth plus y to the fourth is not equal to z to the fourth. Because that has it's not like 10 digits ending. Okay, it only has something like 4 digits ending. Okay, so it's easier for us. We'll try that. Okay, so okay. We attack easier weak spot. Just like a bully. A bully always prey on the weakest person, right? Weaker person. Mathematics, same way. Okay. So you want to attack something that is easier, weaker. All right. So well, that's just how it works. In animal world, a tiger prey upon rabbits. Tiger don't prey upon somebody stronger and bigger like polar bear or grizzly. Okay, so okay, take 5. Okay, just natural world. Okay, food hierarchy, food ecosystem pyramid, triangle. Okay. Where's my jacket? Okay, I'm cooking my lunch. I didn't have any breakfast. I just slept. I mean, vodka, alcohol has same caloric content as carbohydrate or protein. So I guess vodka was my breakfast. Yeah, I know how it sounds. Okay, yeah, miserable. Yeah, sure. Yeah, whatever. Okay, so uh, I want this guy. Very heavy whiteboard. I like this whiteboard. It's heavy. It's so stable because it's heavy. It's very pretty, right? So I'm gonna take a picture of this before I erase. It's pretty. I don't know what the hell we did here, but it's pretty. So I'm gonna take a picture of this before I erase. Okay. Hey. All right. Smile. Smile. Good. Good enough. I took 3 pictures of this. Hey. We find some weak spot, something easy, okay? When n is equal to 4, because looks like yes, lesser number of possibilities there, so we'll do that. Let me grab some nice pen. Right there. Oh, oh. Okay, we'll do red. We'll go red. Big red, okay, so. Where's my water, dude? Let me grab my water. Okay. Let me switch out the drinks. Let me add more drinks. Yeah, I love this quasi semi chaga imitation chaga wannabe mushroom man. Chaga is very rare. Okay, it's not as common as this chef mushroom. Some other kinds. All right. Put this guy over there so that I can see both boards. Okay. So we want to prove x to the 4th plus y to the 4th is not equal to z to the 4th when x, y, z belong to natural number set. Okay, so that's what we are trying to prove. Okay, so this black is kind of weary, so we have to fire this guy. It's no good. We have some thickness, okay, something very thick and strong. Okay, like this one. Very good. Okay, so d0 to the 4th is equal to d prime 0. What do you mean? Some number that ends in 0 when we take it to the 4th is some another number ending in 0. Okay, so and d0 and d1 to the 4th is some other digits previous, okay, preceding digits, and then 1. Okay, we are getting rid of this power. Okay, that's all we are doing. D second to the fourth is some other digits, preceding digits, and 6. Okay, no matter what number it may be that ends in 3, if we take it to the fourth power, it always ends in 1. Okay, so we have period right here, 0, 1, 6. Actually, it's not that. We do one more. Okay, d4 to the fourth is what? D prime 6. Okay, periodicity here is 1, 6, 1, 6. So periodicity is 2. Okay, 0 is some exception, right? So it's like initial condition. Okay, it's very tricky. Okay, so you want to do one more? Okay, d5 to the fourth. Well, that's 5, right? D prime 5. Okay, so we have another exception, huh? Let's keep going, okay? D6 to the fourth. D prime 6. D 7 to the fourth. 1. D prime 1. Okay, so we'll just complete the picture, okay? So 9, 1, 9, 1. Okay. All right. Zero, 1, 6, 1, 6, 5, 1, 6, 1, 6, 1. Okay. So you have 0, 1, 6, and 5, but the complete cycle is 10 digit long. Okay, so it's okay. Well, whatever. It's different approach from, I bet, from what Professor Andrew Wiles did. This old timer, right? He used what, calculus and whatnot. Our approach is not that. Okay, we're taking different approach. We invent notational convention to make it more efficient. Okay, and we do a lot of legwork by making examples. Okay, so our approach, as opposed to traditional professional mathematicians do, we do it different way. Okay, so and it's been working for us very well. So we keep our own tradition of doing things. Brand new constitution, like the Who in England. Yeah, bow down to brand new constitution. Whatever. Yeah, the Who, fantastic English British band, whatever. We can find another counter example here because D3, well, simplest example, okay. Quasi, D1 to the fourth plus, we better label this, okay, subscript like 0, 0, 1, 1, D1, D1 prime, D1, D2, D2 prime, D3, D3 prime, D4, they're different, okay? D4 prime, D5, D5 prime, D6, D6 prime, but they're all different, okay? D7, D7 prime, D8, D8 prime, D9, D9 prime, okay? So D1, 1 to the 4th, plus D5, 5 to the 4th. This becomes what? Let's do it right, okay? So this equals to D1 prime 1. We get rid of this power, okay? So plus D5 prime 5 is equal to D6 prime D6 prime 6 is equal to D6 to the 4th. So we found another counter example that our approach is not working, okay? So it's like love for our enemy, okay? We are loving counter example, okay? So we are being angel's advocate as opposed to devil's advocate. Or devil's advocate, whatever, angels. Devil's devil, I guess that's angel. -1 times -1 is plus, right? We are being very conservative, very conscientious. Okay, so it's not working here either. Oh well. But we keep on trying, okay? So maybe we'll find something, okay? So because we wanted to prove that they cannot be equal, okay? But we found that we realized that they can be equal, okay? So we are making counter example for our own proof to disprove our proof, okay? So okay. Oh well. We're not gonna give up yet, okay? This is interesting. This is fascinating stuff. Yeah. It's mathematically interesting, let alone $1 million. Yeah, it helped us to motivate to do this, investigate this, but it did motivate us. So yeah, they're helping. Okay, $1 million prize by Mr. Bill. Yeah, it's help. He helped. Okay, it gives some juice, some sexiness, mammon, money. You know. Yeah, it does motivate us. It helped. Okay, so he helped. Okay, so God bless him and his family, his progeny. Good man, philanthropist. Okay. All right, but mathematically speaking, it's also very interesting in itself. Okay. So this last digit approach fails. Okay, I guess that's why I gave up when I was 15 years old. It's not quite working. This last digit approach to prove the Fermat's last theorem, it's not working at all. Okay, so but we'll keep on exploring in this direction. At least we can modify it, discover something. It's very interesting. Okay, periodicity of this power operator. Okay, it's just like in Euclidean square, row algebra. There's periodicity there, so it's interesting, very, very interesting. Who knows? Who knows? We may find some brand new algebra. Okay, brand new discovery. All right, very interesting. So any number x, mind you, any number x can be described in 10 different ways. Okay, some d 0, any number in base 10 system, it will end in 0 or 9. Okay, so this preceding digits is, it can be like 1 million, 1 0 0 0 0 0 0. Okay, it ends in 0, or 1,000,009. It's like 1 0 0 0 0 0 0 9. Okay, this preceding digits like 1 0 0 0 0, we call it d0. Okay, this preceding digits, or it could be 9 9 9. Okay, 9. Okay, one, it could be 1 2 3 4 9. That 1 2 3 4, we call it d9. Not deny or denial, but just d digits 9. Okay, any number that ends in 9 whose last digit is 9 is a variable. It could be any numbers. We call it designated as this, with this variable d right foot subscript d9. Okay, so it's a generic variable. Any number that ends in 0 whose last digit is 0. Okay, the preceding digits we designate as d0, d subscript right subscript 0. Okay, it could be 2 3 4 0 or 1 1 1 0. It could be anything. Okay, so that's our invention in notational convention. Okay, we are already making some contribution to mathematics. Okay, so it's good that we are doing this. All right, we are just looking at the very last digit of this number x. It can be any natural number, positive integer. Okay, although we failed in this approach, hey, that's fine. Okay, we rediscovered this periodicity, so that's good enough for us. All right, but we keep continuing after a break. Okay, so we take a break and we get back to this shit. And let me take a picture of this. It's kind of pretty. Okay, so yeah, sexy baby, numbers, mathematics. Yeah, I know how I sound. Sound like fucking loser, right? Nord, geek, Asian, Alaskan, Asian, balding, American, Asian. Alone, yeah. But I'm having fun, I'm happy, okay? I thank God I cannot ask for any more than this. I'm happy. Let's take 5 minutes break, okay? So, alright. At least I know martial arts and some dancing, okay? So. 4 o'clock in the afternoon. It's like early evening. Even on evening, okay, so where's my glasses? Ah. Oh, right there. So, uh, we are conscientious, okay, so we want to be conservative, okay, so we are conscientious people. We have conscience, mathematical conscience, okay, so yeah, it can be equal, okay, it's our counter example to our proof approach, but it's good for us because all we gotta do is to disprove this equality. Okay, then the rest is easy. Okay, we found our weakest link, weak point. If we strengthen that, then everything is fine, right? So we just need to disprove this equality. Okay, so how do we go about it? I don't know. Okay, I do not know, but we're not gonna give up on this. Okay, because this is fascinating problem. Okay, yeah. These six, right? Yeah, the mark of the beast 666 will defeat them. Okay, kinda. Number four in at least in Korean tradition and Korean culture, number four it also same as Chinese character pronunciation of death. Okay, sa number four is pronounced in Korean as sa, and death Chinese character is also pronounced as sa. Okay, sa sa. Okay, so we are encountered with we are fighting this devil. Number six, Michael the Beast, evil number six. It sounds like sex, and sa number four. It sounds like the death in Korean pronunciation of this Chinese character for death. Um, yeah, we are fighting the devil, Satan. We kill it and we eat it. We are snake eaters. We go after the devils, okay, Satans. They are our prey because we are like eagles. We eat snakes or honey badgers, whatever. Snake eating animal, apex predator. Okay, so all right. How do you disprove this shit? This orgy of the devils, number four, number six. Oh, we gotta destroy this satanic orgy. We're gonna arrest them and put them in jail, prison. Mass incarceration. Okay, so. Let's take a break from mathematics. Okay, so if I'm the president ever in United States, yeah, I'm gonna round up and put all these homeless people in jail. There will be mass incarceration. Yeah, many people will say, "Oh, that's unconstitutional. It's punishment against a status of being homeless." I understand that argument, okay, because I went to law school, okay. I took constitutional class because it was mandatory, it was not optional. I know, but constitution, my counter argument to that argument is Constitution does not exist to make America worse, to make the streets dirty, full of urine, human feces, trash, littering. No, that's not how these founding fathers. I don't like that phrase because God is our only father. Okay, so it's anti-Christian. Okay, so to say that, but yeah, just to make it easy, founding fathers, that was not their intention to make America dirty, homeless, trashy, uriny, shitty. That's what homeless people do. We cannot let them do it. Not anymore. Not when I'm the president. I will round them up, and I'll put them in jail. I'll make them work. If they don't want to work, we'll let them starve to death and sell their body parts, human organs, big money. Okay, so if I'm the president, that's exactly what I'm gonna do. We'll discipline them, save them. Okay, so make them better people. Okay, if they want to leave, right, then they will work. If they don't want to work, then they starve to death. Nobody gonna pay for their life. Okay, so kind of useless life anyway. Shitting, trashing, urinating in on the streets. No, not anymore. Not when I'm the president. That's not gonna happen. It will stop. I will stop it. Okay. So until then, yeah, I'll do mathematics. Okay. So how do you disprove this shit? I don't. Did I take a picture of this? Where's my cell phone? I'm gonna open this window. It's getting hot. Man, I haven't ate anything today. No breakfast, no lunch. Just vodka, okay? That's my brunch. Breakfast and lunch. Ah, alone in Alaska. What a loser, huh? Doing mathematics. I'm such a loser. I don't deny that shit about myself. Okay. Yeah. At least I have a job. I have a house, car. Mathematics, sure. Numbers. But my car gave it some service the engine light. So I have to put my car to mechanic tomorrow. Okay, Monday. Yes. Old car, so yeah. So okay, I wrote this down so I can erase it now. Because we got force power that's too high. We do the one less third power. That's the beginning of the famous inequality. That's not equality. Fermat's theorem is about inequality. Okay, so yeah, we'll downgrade once. Okay, because this is too difficult. Okay, so okay. Let me copy it down. Okay, I already took a picture of this. Okay, so but I don't quite want to erase this. I just use different color to copy down. d0 0 to the third is what? d0 prime 0, right? d1 1 to the third is d1 prime 1 legwork. We are getting somewhere, okay? We are discovering something, so just bear with me, okay? Here we go, 666. Or 6666, okay, whatever. Root 66, whatever. All right. 7 times 7 times 7, okay, so it's like 7 times 7 is 9, 4 9. 9 times 7, 63, so it's 3, okay, so that's what this means, okay, so. 8 times 8 times 8. 4 times 8. 2. We are just extracting the very last digit, okay. 9 times 9, 81. 81 times 9, some digit and 9, okay, so we are extracting the last digit, okay, that's what we're doing. I don't know if this approach is going to work to prove Fermat's last theorem, but it's interesting, okay, that's why we are doing, because he has some periodicity there, okay, so. Here we have periodicity of 10. I thought if it is 1616, but it's not. We have 5 motherfucker right here. Okay, so it's motherfucker, asshole. Looks like it's all periodicity 10. Okay, but the selection of digits in this periodicity, yeah, it could be just 1 0 1 6 5 0 1 6 5. You have 4 digits here, and here you have whole digit from 0 all the way to 9. Okay, so alright, well, whatever. Periodicity is powers of natural numbers. Okay, so we're exploring that. So let's make some example. Okay, so you have D1, 1, some preceding digits. We call it D1. Okay, this number ends in 1. Preceding digits we call it D1. Okay, so third plus preceding digits of 2 that ends into any number that ends in 2. Okay, we call it D22. Okay, so okay, so this is equal to D1 prime 1 plus D2 prime 8 is equal to some D9 prime 9. Okay, so that's what each of these correspond to in this table. Okay, yeah, D9 9 cube is D prime 9 9. Okay, so we have to disprove this thing. Okay, so that's our next task. Because according to the Fermat theorem, this has already been proven. We know this is not true. We know this is false, this equality. Because it's already been proven by fantastic professor Andrew Wiles. It's like he's our mother bear, we are cubs. Okay. You know, some birds, what do? They eat fish, and then to feed their chicks, baby birds, they regurgitate this half digested fish. Because that's the only way they can carry this fish. Yeah, some eagles, yeah, they have claws, they catch the fish raw, some mole, rabbit. Eagles, they do that. They carry with their claws, and bring it to their babies in their nest, eagle's nest. Okay. But some other birds, other animals, they cannot quite do that, so they have to eat, digest, and regurgitate, like throw up to eat to feed their babies. Okay, some animals are known to do that. Okay, so like owls, whatever. I don't know. Some birds, some animals. Okay, they do that shit. These animal babies, they eat the vomit, throw up food from their mother or father. Okay, that's kind of what we are doing. Okay, yeah. Professor Andrew Wiles, he already proved this shit. Okay, so we know it's true, and we are taking advantage. We are benefiting. We are in a safe environment. Okay, all we are doing is to find a more easier, more efficient proof of the same theorem that he already proved. So that's what we are doing. Baby mathematicians. Okay, so when he proved this shit, he was like what, in his 60s probably. Yeah, old white guy, Caucasian English gentleman. Okay, and Professor Mr. Andrew Wiles. Okay, so I've never met him. Okay, I've been to England. I have. I've been to Ireland too. I only heard about him, read about him. Okay, so he's cool. Okay, kind of parental figure, I guess. Sure. Okay, so we're baby mathematicians. Okay, we just need to disprove this fuck. How? I have no idea. I'm out of my wits end. I don't know how to disprove this equality, because we know it's false because power is 3, right? They already proved that Fermat's theorem is correct. Conjecture is correct. It's now theorem because they proved it somehow. So some number that ends in 1 and plus some number that ends in 2, we add them together, it cannot be equal to some number that ends in 9 to the cube. Okay, so how to prove that shit? I don't know. Okay, so this last digit approach is not quite working. Okay, but we want to explore this possibility, right? So well, I guess one way to do that is so x is equal to what? D1. What is D1? Ten times D1 plus 1, right? Y is equal to 10 times D2 plus 2. Z is equal to 10 times D9. I'm writing 9 like G. Plus 9, okay, so, okay. D1 is just some bunch of digits, okay? Except the last digit. That's why we have to multiply by 10, okay? 3 times of this shit. Let's do it, okay? So we have 12 minutes left, okay? So x cubed is equal to what? 1000 d1 to the third plus 300 d1 plus 30, d1 squared, 30 d1 plus 1, okay. Y cube is equal to 1000 d2 cube plus 600 d2 squared plus 3 times 4, 12, 120 d2 plus 8. Okay? Yeah, it's just binomial expansion, okay? So I know because I studied mathematics for by now more than 3 decades, okay? For binomial expansion, I know. Okay. This fatherfucker, okay, so Something like that, okay. Well, something like that, okay, so. 10 minutes left. Can this, adding these two guys, can this be equal to this guy? Let's see. This story, by the way, okay, so 30 D1, right? Oh boy. If we add these two guys, can this be equal to this guy? Let's see. D1, D2, D9, they are all arbitrary numbers. Okay, so we may have to go after second digit, third digit, I don't know. I have to think about this. Okay, so we may have to come up with some other theorems. We may have to discover or rediscover some theorems in number theory. Okay, but we can. All right. We are challengers. We love challenges. Okay, we are undaunted. We are brave and courageous. Okay, so we are not intimidated by all these mathematical giants, Goliathans, Gauss, Euler, mathematics professors like Mr. and Professor Wiles. Yeah, they are our parental figures, but we are not scared about them. We believe that we can do better. Okay, that's why we are doing this. Okay. Do I look like Mr. Kim Jong Un? No, I don't want to look like that. I want to have better hairstyle. Okay, so kind of puffy, dry, whatever. I don't want it to be oily. 6 minutes left. We just want to prove this one small thing, that they cannot be equal. Adding these two cannot be equal to this guy. That's the only thing for now that we want to prove. Okay? Let's go about it. Okay, so let's use red. Right? X squared plus y squared is equal to 1000 d1 cube plus d2 cube plus 300, we are factoring it, okay, d1 squared plus 2d2 squared. How beautiful, huh? We're running out of space. Plus 30 times d1 plus 4d2. Okay? Plus 9. Can this be equal to z cube? We want to disprove that shit. We want to prove that they cannot be equal. Yeah, we can do proof by contradiction. Okay, we want to disprove it. We want to prove the inequality thereof. Let's assume the opposite. Let's say they are equal. Then we may come up with some contradiction. Proof by contradiction, okay? we'll take a shot at it. Okay, but after a break, because we ran out of space. I need to find another whiteboard to erase, and that takes more than 5 minutes. Okay, so we have 4 minutes left, so let's just stare at it and think. Brainstorm. Okay, so 243. How the hell did we come up with this fucking number, man? I don't know. 3 times 3 times 3, whatever. What? 81 times 3? Okay. 81 times 3, that's 9 times 9 times 3, that's whatever. 3 to the 5th, okay. How about 729? How the hell did we come up with that fucking number? I don't know. Yeah, it's multiple of 9, obviously. So 9 times 9 times 9 times 9, I guess. I don't know. No, it can't be that. So 9 times 9 times 9. I think that's what this is. Okay, so 81 times 9. Maybe. Okay. Yeah, I think that's what it is. Okay. 9 to the 3rd. Okay, so we pick on smaller guy, just like a bully, just like a predator, just like animal, just like herbivorous animal. They will pick on the smaller guy, right? So okay. This guy and this guy. Okay, that's what we're gonna focus on. Okay. It will fail. It may fail. It may succeed. We don't know. Okay. Because this guy is what? I mean, different color. We have 1 minute left. Okay, so 722. Okay, so 720 plus 9, right? So 720 have to be absorbed in these other terms. Is it multiple of 30? Yes, unfortunately. Okay. All we want to prove, little baby step at a time. Okay, all we want to prove is that this guy is not equal to Z3. Okay, that's all we want to prove here. Okay, so little baby step at a time. We'll build up from here. Okay, so but even this is not that easy. Okay, because it can be absorbed to these some other terms. But hopefully we get there. I don't know. I cannot be too sure. I mean, come on. I cannot be too sure. Okay, so but we'll take a shot at it. We'll at least try whether it works or not. Just like I learned in U.S. Army, you try it anyway, whether it's gonna work or not. Okay, because that's the order. Okay, that's divine order. Thank you. We'll see you soon. Bye.